everybody, welcome back to the channel. So today we're going to continue on with the gas laws, and we're going to talk about the combined gas law as well as Dalton's law of partial pressures. So the combined gas law really could have been in the video before this, but that video was already like a half an hour long, so I didn't want to put it in there. But the combined gas law literally takes Boyles's law, Charles's law, and Gay-Lussac's law and puts them all together. So you might remember, well, hopefully you remember, that every one of those equations kept one variable constant. So whether it was pressure or volume or temperature, something was constant. In this case, the combined gas law has nothing constant except the number of moles of the gas, which we're not going to get into that. But pressure, volume, and temperature are all changing. So it might sound like this equation is like really complex when in fact, it's literally every one of those equations put together. So the combined gas law expresses the relationship between pressure, volume, and temperature of a fixed amount of a gas. So the fixed amount just means that the number of moles is not changing. And your equation looks like this. So it's P1 V1 over T1 equals P2 V2 over T2. So like I said, it's literally all three laws put together. You'll see without temperature, you have just Boyles's law right here on the top. You see you have Charles's law if you take away the pressure components on both sides. And then you have Gay-Lussac's law if you take away volume. The combined gas law really works for everything because if you think about, let's say, Boyles's law, if temperature is constant, so let's say you have some system where the pressure and volume is changing, but the temperature stays the same. If temperature, let's say, is 298 Kelvin on the bottom of both of these sides of the equation, they're going to cancel out anyway. So that's where Boyle's law comes into play. So really everything is the combined gas law, but if you're keeping something constant, you don't have to express it. Boyle's law actually came first, and then after the other relationships came into play, then we discovered that this is in fact true. But anyway, the combined gas law is actually useful for when we want to correct something for STP. So you might remember me talking about STP in one of the earlier videos, and I was saying how, oh, well, if we do this reaction here and we collect some amount of a volume of a gas at our temperature and our pressure, what volume of gas would somebody in Hawaii collect at their pressure and their temperature? We could figure that out by using the combined gas law. So if we have our volume of a gas that we collected, whatever that may be, and we have our pressure and temperature conditions, we could figure out what volume would that be at a different set of pressure and temperature conditions. And you can even find out what volume of gas would have been collected at STP at 1 atmosphere and 273 Kelvin. So you're actually going to use the combined gas law quite a bit for when we're correcting for STP. What's the volume at STP, those standard conditions, if we collected a certain volume at a non-standard set of conditions, like what we would do in the lab? So knowing all of that information, let's go ahead and try sample problem 5. A volume of gas, so I'm going to take each of these here and just kind of write the workout like I normally do. A volume of gas occupies a volume of 27.5 milliliters at 22.0 degrees Celsius and a pressure of 0.974 atmospheres. What would be the volume? So volume's what we're trying to find at these new conditions of 15 degrees Celsius and a pressure of 0.933 atmospheres. Like I say, you don't have to write this out every time, but sometimes it helps students to write all the variables out as they go through. So I don't have any of those constant. Volume's not constant, neither is temperature nor pressure. So I do have to use the combined gas law here. We do have to convert units of temperature to Kelvin as always. So if I add 273 to this, 22 degrees Celsius is 295 Kelvin. And 15 degrees Celsius is 288 Kelvin. So let's just plug all of our variables in to the combined gas law equation and then solve. So 0.974 multiply that by the volume, which is 27.5, and divide that by the temperature, which is that 295 Kelvin. And let's set that equal to our second pressure. So I'm changing the conditions, 2.933. I want to find the new volume at the slightly lower temperature of 288 Kelvin. Again, I think the hardest time students have with this is just plugging this into the calculator correctly. So if you don't get this answer, that's fine. Just double check yourself in the calculator or ask me a question. I'll be more than happy to help you type this correctly in there. But when you solve this correctly, you should get 28.0 milliliters. It's a little hard, in my opinion, to kind of guess whether or not the volume is going to go up or down, especially because you have so many conditions changing. You might be able to predict it, but if you don't have to predict it, then just don't, because it's sometimes harder to do that. So you go ahead and try sample problem B. This does have a gas at STP, so see if you can do this one on your own. So here is the answer for B. In this case, you have 700 milliliters of a gas at STP, so you know the conditions. The temperature is 273 Kelvin, and the pressure is 1 atmosphere. You might notice that I used units of pascals here, and that's because rather than doing a conversion at the end, I could just look on that chart and find what is 1 atmosphere of pressure equal to in pascals, because I'm going to need to find my answer in pascals anyway. If you used atmospheres here and then got units of atmospheres for your answer and then converted it, that's fine. You should get the same exact answer. What you're going to notice in chemistry is that there are so many ways to solve problems, and as long as your method makes sense logically and experimentally, then by all means do it. So then we have our side equal to those values right there. We have this volume, 303 Kelvin, solve for pressure, and you should get 3.93 times 10 to the 5th pascals. Let's dive into Dalton's law of partial pressures next. So now let's get into Dalton's law of partial pressures. I don't know why, but students always hate Dalton's law. And it's really, again, pretty self-explanatory, but I think for certain problems, students just forget to use Dalton's law. So hopefully we'll do enough practice in class where you're not forgetting to use Dalton's law where it's appropriate to. But Dalton's law of partial pressure states that the total pressure of a mixture of gases is equal to the sum of the individual, which we know as the partial, pressures of all the component gases. So right now, the air that you're breathing is a combination of a lot of different types of gases. So it's comprised of mostly nitrogen gas, but there's some oxygen, there's some carbon dioxide, there's a little bit of water vapor in there, and there's some trace amounts of some other gases. And if you look on your phone, you can find the barometric pressure for the day. So it's usually about like 30 inches of mercury. And we can convert inches to millimeters of mercury, which we can then convert to atmospheres or whatever units you want, really. This total pressure that we are at is really a combination of the total pressures of each individual gas. So right here, this is what this expression is saying, that the total pressure of a mixture, so in this example, the air that you're breathing, the total pressure of the atmosphere is equal to the sum of all of the pressures of the individual gases. So this would be the pressure of the first gas. This would be the pressure of the second gas. So maybe this is nitrogen, the pressure of oxygen, the pressure of water vapor, carbon dioxide, et cetera, et cetera. It doesn't matter how many gases there are. I think students get very like, oh my God, what is that like? What do these dots mean at the end? How many gases are there? I mean, you could have a system with 50 different types of gases, which we're not going to use because that's very uncommon. But it doesn't matter how many gases make up that mixture. All it's saying is that the sum, the total pressure of that mixture is equal to the sum of all the component gases there. So let's go ahead and take a look at this example. So right here, I have some gas, right? And this gas, we're just going to call it P1, is at some pressure. And it looks like here that this gas is at 1. Again, there's no units here for this. We're just going to say 1 atmosphere. Pressure is very low because these particles are relatively far apart. They're not hitting the walls of the container very frequently. So the pressure is low. If I look at this second gas, which we're going to call the gas at the second pressure, P2, we have a lot more gas particles that are in there. And therefore, in this volume, the pressure is much higher. So we'll see here it's actually double. So 2 atmospheres, we'll say. If I combine these two gases in the same exact vessel that is the same volume, because the volume isn't changing, what's happening is when you put them together, the total pressure is equal to the sum. If I take this gas and combine it with this gas into one system, those particles are hitting the walls of the container more often because there's more particles in the system. So the total pressure is equal to the sum of both of the individual pressures. And if I look at that, we'll see that this little gauge tells us that we would have a total pressure of 3 atmospheres because the 1 plus 2 gives us the 3 atmospheres there. And that's Dalton's law of partial pressures. It's really not difficult. Let's go ahead and try the next sample problem in the notes, taking just this very basic concept and putting it to use. So sample problem 6, a metal tank contains 3 gases. So it has oxygen, helium, and nitrogen. If the partial pressures of the 3 gases in the tank are 35 atmospheres, 5, and 25 atmospheres, what is the total pressure? So you could do this very easily, but I just want to show you where this is coming from. So PT is the total pressure. And the total pressure inside the tank, because this tank contains only 3 gases, that's equal to the partial pressure, in this case of oxygen. So I have my partial pressure of oxygen plus my partial pressure of helium plus the partial pressure of nitrogen. So you have to have those 3 P's there because, of course, the tank contains 3 gases. So if we want to know what's the total pressure, all I have to do is just add up the partial pressures of the component gases. So it says here, oxygen is 35 atmospheres. The helium is 5 atmospheres. And then the nitrogen is 25 atmospheres. The total pressure would just be the sum, which is 65. That's a very basic example of Dalton's law of partial pressures. Why don't you try sample problem B? This one you actually have to solve for one of the partial pressures in there, and you're given the total. So go ahead and try this one. And there's your answer for this one. So you were solving for one of the variables on the right-hand side of the equation here, and you were given the total pressure. So the total pressure is 0.99 atmospheres, and you have the partial pressure of CO2, your partial pressure of hydrogen sulfide. You wanted to know what's the pressure of the remaining air in that system, and your answer is 0.92. So I wanted to introduce, after going over the basics of Dalton's law, just another example, kind of using algebra to think about another way of solving this. So the partial pressure of each gas in a mixture is equal to the mole fraction of each gas multiplied by the total pressure. So in this case, X is equal to some gas. So let's just go ahead and make a note of this here. So X is equal to some gas. That gas could be hydrogen, it could be helium, it could be carbon dioxide, whatever. If I want to know the partial pressure of that gas, so this is the partial pressure of some gas, that pressure of that gas is equal to the moles of that gas divided by the total moles of gas in the system multiplied by the pressure, the total pressure of the system. So it's almost like you're using just a fraction here. If I know that this system is, 20% of this gas, what's 20% of the total pressure? It's what we're trying to solve here. It's a different way of thinking about this. So let's try sample problem 7 together. A mixture of 40 grams of oxygen and 40 grams of helium has a total pressure of 0.9 atmospheres. What is the partial pressure of each gas? So I'm not given anything else other than the pressure of the system and then just the number of grams of each gas that's there. We can find out, just based on this information, what's the partial pressure of each individual gas. But of course, in chemistry, you always have to convert to the number of moles. So let's convert to the number of moles of oxygen and the number of moles of helium. I'm going to keep this short, so you go ahead and do that, and then we'll jump back into the next part. So here are the number of moles of each gas just by doing a simple mole conversion. So I have the individual number of moles of each component gas. However, in order to find the partial pressure, I do need to find the total moles of the gas in the system. So I'm just going to go ahead and add those two together. Of course, with significant figures, you should have only one place after the decimal. So I'm going to round this to 11.3 moles of gas total. So let's go ahead now and find what's the partial pressure of just oxygen. So I have PO2. I'm going to set X equal to O2 because I'm trying to find the partial pressure of just oxygen. So I know that this system contains 1.25 moles of oxygen. And the total moles of the gas in the system is 11.3 moles. I'm just going to put 11.3 moles, T for total. And the total pressure in the system, both of these gases has a total pressure of 0.9 atmospheres, 0.900. So it's almost like a percentage. So you know that 1.25 of the 11.3 moles of that gas is oxygen. And if you multiply that percentage by 0.9, you should find that just the oxygen would exert a pressure of 0.0996 atmospheres. So oxygen exerts a pressure of 0.0996 atmospheres. Let's try it for the helium now. So let's find the partial pressure of helium. We want to know, what does that exert? Let's use the 10 moles of helium on top, divide that by the total, moles total, times that 0.900 atmospheres. Now, of course, there's a heck of a lot more helium in this system, so it should exert a much more significant pressure. And you'll see that when you solve for this, that's in fact what you get. And your answer should be 0.796 atmospheres. Now, you didn't even have to do that second step because you know the total is 0.9. So if you have a total of 0.9 atmospheres, and if your oxygen exerts a pressure of 0.0996, if you subtract that, you should get something relatively close to 0.796. Now, when I did that, I get 0.8, but I think it has to do with significant figures, which we're not going to worry about getting differences in answers with significant figures. But you should get the same exact thing. So you didn't have to do this step here because you know if the total is 0.9 and if oxygen is 0.0996, the helium must exert whatever the difference is between those two. So, and of course, the helium pressure is going to be much more significant in the system than the oxygen because helium takes up a heck of a lot more moles than the oxygen does. So the mass doesn't matter. It all comes down to the number of moles of the gas. B is actually a little bit easier than this one before it. So a container with two gases, helium and argon, contains 30% by volume helium. Calculate the partial pressure of helium and argon if the total pressure inside is 4 atmospheres. So we know that this system, this container, contains helium gas, and it also contains argon gas. So we do know the total atmospheric pressure here, but what's important is that we do know that this gas or that this system is 30% by volume helium. So if the only other gas is argon in this system, I don't know what that pink thing is right there. That's interesting. This must be 70% argon by volume because there's only other one gas in there. So if I want to know what is the partial pressure of each gas, all I have to do is just multiply that value by 4. The only thing is that this is in a percentage, and we don't want it in the percentage here. We actually want to divide it by 100 because we want just the fraction, the decimal version of that. So to solve for this, we know 0.300 percentage of that is helium. I'm going to multiply that by 4 atmospheres. And when I do that, I get 1.2 atmospheres. Let's tack another sig fig on there. So in this whole entire system, 1.2 atmospheres of that is helium gas. Again, you could figure out the pressure of just argon by subtracting from that. Let's go ahead and just double check. So if the total pressure of this system is 4 atmospheres total, and if 1.2 atmospheres of that is helium, you could easily figure out how much argon would be present there just by doing that quick subtraction. I forgot that significant figure again, darn it. So to find that out, you should have 2.80. And if you were to actually do what we did above, so using that 0.700, multiply that by 4 atmospheres, you should get the same exact thing. So like I said, ultimately, it doesn't matter how you solve the problem as long as your technique makes sense mathematically and using chemistry topics. This takes a little bit of practice. This kind of stuff is really important in AP chemistry, which is why I wanted to just touch on it here, because I noticed that a lot of problems in AP come down to this particular topic right here, having to do with the moles of the gas and what's the partial pressure given the moles and the total pressure of the system. So if you're going to take AP chemistry, I would put a nice big star next to this section because this is important when we talk about gas laws. So Dalton's law becomes cumbersome for students because they forget about this little step right here. And it has to do with actually collecting gases in a laboratory setting. It's very difficult to collect gases, of course, because they are very far apart from one another, and because they have so much energy, they're hard to contain within one system. So one way that chemists can actually collect gases is by using a method called water displacement. So water displacement is an effective method for chemists to collect gases during experiments. And you're going to do a lab very similar to this, actually not using zinc, but a piece of magnesium instead, where you'll collect a gas over water. So we have this particular vessel right here. We have some reaction, and this reaction is producing a gas. So this is a single replacement reaction, and we are producing hydrogen gas. We're collecting that gas by letting it bubble into this test tube through this tube here. So you can see the hydrogen gas that's going through the tube. And I'm collecting it through water. So of course, the gas is going to flow through the water because since it's less dense, and it's going to come up over here. So you can see that's exactly what's happening here. The tube is letting the hydrogen gas escape. And we can measure how the volume of gas that's collected. If this had graduations on it using a burette, we can do that. However, we have to remember that at any temperature, even at room temperature, water is also evaporating. If you leave a glass of water out on the table, although it's going to take a long time, that water is evaporating a little bit every day. The surface of that water is exerting a pressure on the surrounding environment. So inside this system, when this is happening, you have not only hydrogen molecules that are present within this area, but you also have water molecules because those water molecules are evaporating, right? Because water evaporates even a little bit at room temperature. And when that water evaporates, this water is also exerting some pressure on the inner walls of this container. Granted, it's not a lot, but we have to consider that when we are trying to figure out the pressure of just the hydrogen gas that we collected. And the pressure of the water is dependent on the temperature. So of course, the higher the temperature, the more those water molecules are evaporating, which means the more that are present in the system, which means the higher the pressure. And we can calculate what is the pressure of just the gas that's collected. What's the pressure of just the hydrogen gas? Because it's not going to be equal to atmospheric pressure because we also have some water vapor molecules that are in there. So we can use this kind of second form of Dalton's law of partial pressures. It's still Dalton's law. It's just a variation of it for this particular method of collecting gases. So atmospheric pressure, that's what this is right here. That would be whatever the barometer reading is for that day. You can find that on your phone, on your weather app, is equal to the pressure of the dry gas, So when we say dry, that just means without the water vapor. So that's just the gas in question. So this, for example, would be just that hydrogen gas. So the pressure of just that hydrogen gas plus the pressure of water vapor at some temperature. And we can figure out that temperature by looking at a chart. So you could just take the temperature of the water using a thermometer, and we'll assume that that's also the temperature of the gas. We're going to do a couple of labs with this, so you'll see how this works in real life. But we can determine what is the water vapor pressure at a certain temperature by looking at this particular table. So room temperature is usually about like between 21 and 22 degrees Celsius. So normally you're going to have to use either one of these numbers. At room temperature, water vapor has a pressure of about 18.1 or 18.6 millimeters of mercury and of about 2.49 kilopascals. So just notice there's two different units here, and you might have to convert these units to something else depending on what the problem is giving you barometric pressure in. So you would use this to subtract that value from the atmospheric pressure to get the pressure of just the dry gas, whatever you're collecting. So whether it's hydrogen gas, maybe you're collecting oxygen gas. It just depends. Let's go ahead and try the sample problems with this section of Dalton's law, and then we'll call it a day for this video. So sample problem 8. Hydrogen gas is collected over water at 20 degrees. On that day, the barometer measures an atmospheric pressure of 30.2 inches of mercury. What is the pressure of the hydrogen gas collected? So we do want just the hydrogen gas in this case. And we consider this hydrogen gas is dry right here. So this is the dry hydrogen gas, usually in quotes like that. This is an example of something you would find very readily in an experiment. You're going to do this in class quite a few times, not only in problems, but also in the couple of labs that I have. So let's go ahead and solve for this one. What is the pressure of the dry hydrogen gas collected? So I do have to use Dalton's law of partial pressures for water displacement. And this says that the total pressure, atmospheric pressure, is equal to the partial pressure of the dry gas plus the partial pressure of water vapor at some temperature. I'll just put at T there. What we need to do first is we got to get out of inches of mercury, because if I want to look up the partial pressure of water at some temperature, we're not given units of inches of mercury here. So we're going to actually convert inches to millimeters just using a basic conversion, a basic measurement conversion. Even though it's in inches of mercury, it doesn't matter because we're still converting inches to millimeters. So let's go ahead and do that. 30.12 inches of mercury. And I just did a quick Google search here, and I found that 1 inch is equivalent to 25.4 millimeters. And again, it doesn't matter because it's still inches to millimeters. You don't have to put the HG there, but you can if you want. And when you solve for that, your answer should have, let's do 3 significant figures, 765 millimeters of mercury. So this is the total pressure. So this is PT that we just converted into different units. Let's look on the chart and find what's the pressure of hydrogen at 20 degrees Celsius. So if I look on this chart here, at 20 degrees Celsius, water exerts a pressure of 17.5 millimeters of mercury. So let's just write that down. The partial pressure of water at 20 degrees Celsius is 17.5 millimeters of mercury. Now that I have those two components, we can find the pressure of just the dry hydrogen gas. So I have our atmospheric pressure. Actually, this right here is not just PT, but it's atmospheric pressure, because that's what the barometer is reading that day. So 765 millimeters of mercury is equal to the partial pressure of the dry hydrogen plus the partial pressure of the water at 25 degrees, which I have as 17.5. And if you do a simple subtraction, you should get 747.5. But with significant figures, your answer should be 748 millimeters of mercury. So that's the pressure that that hydrogen is exerting in that particular system. Let's try sample problem B, a little bit different. So in this case, 45.9 milliliters of oxygen was collected over water at 24 degrees. The barometric pressure that day was measured to be 772.3 millimeters of mercury. What volume would the gas occupy at STP? So the volume of the gas that we've collected, that 45.9, is not at STP. It's at 24 degrees and 772 millimeters of mercury. So we have to, and it was collected over water. So anytime you see this phrase over water, you know you're going to have to use Dalton's law of partial pressures. I normally tell my students, anytime you see over water, underline it, because you know you're going to have to use Dalton's law of partial pressure somehow. So we actually have to use Dalton's law of partial pressures first, and then use the combined gas law to figure out what volume would this gas occupy at STP. So let's actually use Dalton's law first to find out what's the pressure of just the dry gas, of just the dry oxygen gas, because this is not the pressure of this gas right here. It's actually less than that because we have to consider water vapor pressure. So we'll say step one is use Dalton's law. Dalton's law. Because we're doing a water displacement here. So and I don't have to do a conversion here because that's already in millimeters of mercury, which is nice. And we can find the pressure of the dry oxygen gas. And let's look up the pressure of water at 24 degrees. So I scroll up here, and in the correct units of millimeters of mercury, it looks like it's 22.4. So I'm going to add 22.4 to this right here. Millimeters of mercury. And if I solve for the partial pressure of oxygen, you should get 749.9. 749.9 millimeters of mercury. So this is the pressure of just that oxygen gas without that added water vapor in there. However, the question is not asking us for that. The question is asking what volume is the gas at STP. So we want to know what's the volume at standard temperature, which is 273 Kelvin, and at standard pressure, which is 1 atmosphere. We have all of these initial conditions. We have, so let's have here, so we're going to use combined. I don't know why I forgot to write that. Use combined gas law. I have my V1. That's this 45.9. That's the volume of the gas that we collected, 45.9 milliliters. I have the second temperature, so it's at 24 degrees. 24 plus 273 gives us 297 Kelvin. I'm just saving some room here, so I'm not writing the workout. And I also have the initial pressure, the pressure of just the dry gas. Remember, just the dry gas is 749.9 millimeters of mercury. So we're correcting it for STP. That's what this is known as. So I'm going to write that in a different color down here just because you might hear that phrase. This is called corrected to STP. Now let's plug everything in and solve. Notice how the units of pressure is not the same. So I'm just going to make my life easy, and I know 1 atmosphere is equal to 760 millimeters of mercury. So we're just going to start from there. Let's plug in 45.9 times that 749.9 over 297. And I want to know what's the volume at 760 millimeters of mercury and 273 Kelvin. Like I said, as long as you type this in the calculator correctly, you should get an answer of 41.6 milliliters. If you're having a hard time getting the answer, don't forget to ask me a question, how to type it into the calculator. Like I said, it's an easy fix. It's nothing to get overwhelmed with. That is Dalton's law of partial pressures and the combined gas law. Of course, if you have any questions, stop by and see me. Don't hesitate. And otherwise, I will see you in the next video, which is all about Avogadro's law and the standard molar volume of a gas. So I will see you then. Have a good day.